Good day, everyone. Today, we will begin our discussion on Chapter 35 Interference, one of the most fascinating topics in wave optics. Interference is a phenomenon that occurs when two or more waves overlap and combine, producing regions of reinforcement and cancellation. This topic is historically significant because it provided some of the strongest evidence that light behaves as a wave. Prior to the 19th century, scientists debated whether light was composed of particles or waves. Through experiments involving interference, scientists observed patterns that could only be explained by wave behavior. Throughout this chapter, we will investigate how light waves interact, how interference patterns are formed, and how these principles are applied in modern technology. By the end of this lesson, you should be able to explain the mechanism behind interference and recognize its importance in both scientific research and everyday applications. So, moving on, before we dive into the details, let us first examine the learning objectives of this chapter. So first is to consider the interference of waves in space. Second is to analyze two source interference of light. Third is to calculate the intensity of interference patterns. Then to understand interference in thin films. And lastly, is to use interference to measure the extreme small distances. So, for the introduction, let us begin with a simple observation from everyday life. Have you ever looked at a soap bubble and noticed its beautiful rainbow colors? Interestingly, soap itself is colorless, yet the bubble displays brilliant shades of blue, green, yellow, and red. Similarly, DVDs and CDs often exhibit multicolored reflections when exposed to white light. This phenomena occur because of interference. When light waves reflect from different surfaces, they overlap and interact with one another. Depending on phase relationship between the waves, some wavelengths reinforce each other while others cancel out. This selective reinforcement and cancellation produce the vibrant colors that we observe. These effects provide compelling evidence that light possesses wave-like properties, which is the central theme of our discussion today. To understand interference, we must first understand wave propagation. Imagine dropping a stone into a calm pond. Circular waves spread outward from the point of impact, carrying energy through the water. In a similar manner, light waves spread outward from a source. The figure shown on this slide illustrates wave fronts, which are imaginary surface connecting points that oscillate phase. An essential principle governing wave behavior is the principle of superposition. This principle states that when two or more waves occupy the same region of space, the resultant displacement at any point is equal to the sum of the individual replacement displacements. In other words, wave pass through one another without losing their identities. This principle is fundamental because interference patterns arise directly from the addition of wave amplitudes. Without superposition, interference could not occur. Now that we understand superposition, let us explore the two primary types of interference. The first is constructive interference, which occurs when two waves arrive in phase. This means that the crest of one wave aligns with the crest of another wave, and the trough aligns with trough. As a result, their amplitudes add together, producing a larger resultant wave. Constructive interference occurs whenever the path difference between the waves is an integer multiple of the wavelength. The second type is destructive interference, which occurs when the crest of one wave aligns with the trough of another wave. In this case, the waves partially or completely cancel each other. Destructive interference occurs whenever the path difference is an odd multiple of one half wavelength. Understanding these two conditions is essential because every interference pattern consists of alternating regions of constructive and destructive interference. Now, moving on, so as you can see in this slide, illustrates the interference pattern produced by two coherent wave sources. Coherent sources are sources that emit waves of the same frequency and maintain a constant phase relationship. As the waves spread outward from the two sources, they overlap in different regions of space. In some locations, the wave arrives in phase and produces constructive interference. In other locations, they arrive out of phase and produce destructive interference. The result is a series of alternating regions of reinforcement and cancellation. Notice that the pattern exhibits symmetry because both sources emit waves with identical properties. This type of interference pattern is commonly observed not only in light waves, but also in sound waves and water waves. As we continue examining the interference pattern, we can clearly identify regions where constructive interference consistently occurs. These regions form not what are known as antinodal lines, where the wave amplitude is always relatively large. Between these antinodal lines are nodal lines where destructive interference occurs and the resultant amplitude remains near zero. The existence of these stable patterns demonstrates the predictable nature of wave interactions. If the sources were not coherent, the interference pattern would fluctuate randomly and become difficult to observe. Therefore, coherence is a crucial requirement for producing observable interference effects. This concept becomes especially important when studying light interference in laboratory experiments. So one of the most famous experiment in physics is Young's double slit experiment, which provided convincing evidence that light behaves as a wave. In this experiment, light passes through two narrow slits separated by a small distance. Each slit acts as a new source of coherent light waves. As these waves spread outward and overlap, they interfere with one another. A screen placed between the slits displays a series of bright and dark fringes. Bright fringes correspond to constructive interference. If light consisted only of particles traveling in straight lines, such pattern would not appear. Therefore, the double slit experiment remains one of the strongest demonstrations of the wave nature of light. The interference pattern observed on a screen depends on several important variables. These include the wavelength of light, the distance between the slits, and the distance from the slits to the screen. The position of each bright fringe can be calculated using the interference equation derived from geometry. As the wavelength increases, the fringes become farther apart. Likewise, increasing the distance to the screen also increases fringe spacing. On the other hand, increasing the slit separation decreases the distance between fringes. These relationships enable scientists to determine unknown wavelengths with a high precision. The mathematical analysis of interference patterns demonstrate the predictive power of wave theory. So as you can see here, this example demonstrate how interference measurement can be used to calculate the wavelength of light by measuring the position of a bright fringe, the slit separation, and the screen distance. We can substitute these values into the interference equation. Through careful calculation, the wavelength can be determined accurately. This method is significant because it allows experimental verification of theoretical prediction. It also illustrates the close relationship between mathematical and physical observation. In many university laboratories, students perform variations of this experiment to determine the wavelengths of different light sources and gain first-hand experience with interference phenomena. So, as you can see here in this slide, it demonstrates that interference is not limited to visible light but occurs throughout the entire electromagnetic spectrum. In this example, two radio towers separated by a distance of 400 meters emit radio waves at a frequency of 1500 kilohertz while oscillating in phase. As the waves travel outward, they overlap and interfere with one another, producing regions of constructive and destructive interference. Constructive interference occurs in direction where the path difference between the waves is an integer multiple of the wavelength, resulting in stronger signal intensity. Conversely, destructive interference occurs where the path difference is a half integer multiple of the wavelength, reducing signal strength significantly. This principle is widely applied in communication engineering, where antenna arrays are designed to maximize signal coverage in specific direction while minimizing interference in others. Up to this point, we have focused on the location of bright and dark fringes. But now we must understand why these fringes have different brightness levels. The intensity of an interference between the patterns depends on the phase difference between the interfering waves. Using the principle of superposition, we combine the electric field vectors of the two waves through a graphical method known as a phasor diagram. Applying vector addition and law of cosines allows us to determine the resultant amplitude of the combined waves. Since light intensity is proportional to the square of the electric field amplitude, even small changes in phase difference can produce significant variations in brightness. This analysis enables us to predict the intensity distribution across the entire interference pattern, not just the location of maxima and minima. So, as you can see here in this slide, extends our analysis by relating phase difference directly to the path difference. So recall that whenever the path difference between two waves increase by one wavelength, the phase difference increases by 2 pi radians. Using the geometry of the double slit arrangement, we can express the path difference in terms of a slit separation and observation angle. Substituting this relationship into the intensity equation yields a mathematical expression that predicts the brightness at every point on the screen, resulting the intensity distribution explains why bright fringes are separated by regions of gradually decreasing intensity rather than abrupt transitions. This quantitative treatment of interference allows physicists to compare theoretical predictions with experimental observations accurately. Such calculations are fundamental in optical engineering and modern photonics. Interference sources. So this as you can see in this slide, it's visually reinforce the relationship between interference and intensity distribution. Notice that the brightest region occur where the constructive interference is the strongest, indicating maximum amplitude and therefore maximum intensity. Between these bright regions are dark fringes, where destructive interference causes the intensity to approach zero. The gradual variation in brightness between maxima and minima reflects the continuous change in phase difference across the observation screen. This pattern provides a clear demonstration of how waves' properties determine observable light intensity. Understanding intensity distribution is particularly important in application involving lasers, optical sensors, and precision measurement systems. Interference can also occur when light interacts with extremely thin transparent layers known as thin films. When light strikes a thin films, part of the wave reflects from the upper surface while another portion penetrates the film and reflects from the lower surface. These reflected waves travel distances before recombining, creating condition for interference. Depending on the thickness of the foam and the wavelength of light involved, some colors may undergo constructive interference, while others experience destructive interference. This selective enhancement and cancellation of wavelengths produce the vibrant colors observed in soap bubbles, oil films on water, and insect wings. Thin film interference demonstrate how wave interaction can create visually striking effects from otherwise colorless materials. An important concept in the thin film interference is the phase shift that occurs during reflection. When light reflects from a boundary leading to a medium with a higher refractive index, the reflected wave undergoes a phase shift of pi radians, equivalent to half a wavelength. However, when light reflects from a boundary leading to a lower refractive index, no phase shift occurs. These phase changes alter the interference condition and must be considered carefully when analyzing thin film problems. Failure to account for reflection-induced phase shifts often leads to incorrect predictions of constructive and destructive interference. Therefore, understanding phase reversals is essential for accurately interpreting interference phenomena in optical systems. Moving on, which between two places. So this slide introduces the phenomenon of interference in a wedge-shaped air formed between two slightly inclined plates because the separation between the plates changes gradually along the wedge. The thickness of the air film also varies continuously as light reflects from the upper and lower surfaces of air wedge. Interference occurs, producing a series of alternating bright and dark fringes. The spacing of these fringes provides valuable information about the geometry of the wedge and the wavelength of light used. Scientists and engineers frequently use wedge interference patterns to measure extremely small distances and evaluate the flatness of optical surfaces. This technique illustrates how interference can serve as a highly sensitive measurement tool. Now, moving on for the Newton's rings. So Newton's rings are a classical example of interference produced by a thin air film. They occur when a curved lens is placed on top of a flat glass surface, creating an air gap whose thicknesses increases gradually from the center outward. As light reflects the two surfaces of two air film, concentric rings of constructive and destructive interference appear. These rings alternate between bright and dark because the film thickness changes gradually or continuously with distance from the center. Newton's rings provide valuable information about lens curvature, wavelength, and surface quality. So, this phenomenon remains one of the most important demonstrations of optical interference in both teaching laboratories and research settings. So moving on in the using interference fringes to test a lens. So one practical application of interference is the testing and evaluation of optical lenses. In this method, a lens being tested is placed in a contact with interference lanes of known quality. So as you can see in the picture provided, so if the surface match perfectly, very few interference fringes will appear. However, any imperfections, scratches, or deviations in curvature create variations in the air gap between the lenses. resulting in invisible interference patterns. So, by examining the shape and distribution of these fringes, technicians can identify defects with extremely high sensitivity. This method is widely used in optical manufacturing to ensure that lenses meet strictly quality standards. It demonstrates how interference can reveal imperfections that are far too small to detect by ordinary observation. Now, moving on to non reflective coatings. So, many optical devices, including cameras, microscopes, telescopes, and eyeglasses, um, use non-reflective coatings to reduce unwanted reflections. These coatings consist of a thin, transparent films carefully chosen so that reflected light waves interfere destructively. So, when destructive interference occurs, the reflective waves cancel each other, minimizing glare and maximizing the transmission of light through the lens. The thickness of the coating is typically designed to be 1/4 of the wavelength of the target light. As a result, image brightness and clarity are significantly improved. This application demonstrates how interference principle can be used to solve practical problems and enhance the performance of modern optical technologies. So the Michelson interferometer is one of the most precise optical instruments ever developed and represents a major application of interference. In this device, a beam splitter divides a single light beam into two separate paths that travel different distances before recombining. When the beams meet again, they interfere, producing a pattern that is highly sensitive to even the smallest changes in path length. By analyzing shifts in the interference fringe, scientists can measure wavelengths, refractive indices, and distances with extraordinary precision. The Michelson interferometer has played a crucial role in the development of modern physics and precision meteorology. Its underlying principle continues to be used in advanced scientific instruments, including the laser interferometers employed in gravitational wave observatories such as LIGO or the LIGO. So, for the summary of the chapter 35 about interference, interference is a fundamental wave phenomenon that occurs when two or more waves overlap and combine according to the principle of superposition. Depending on the phase relationship between the waves, interference may be constructive, resulting in increased amplitude and intensity, or destructive, resulting in partial or complete cancellation. Double slit experiment provide compiling evidence for the wave nature of light by producing alternating bright and dark fringes on a screen. The position and spacing of these fringes depends on factors such as wavelength, slit separation, and distance to the screen, allowing scientists to analyze and measure the properties of light with great accuracy. The chapter also explored how interference affect the intensity of light and how it occurs in thin films, producing colorful patterns seen in soap, bubbles, oil slicks, and other everyday phenomena. Important concepts such as phase shift during reflection, Newton's rings, and wedge-shaped air films demonstrate how interference can be used to study and measure extremely small distances. Practical applications include testing optical lenses, designing non-reflective coating for optical devices, and using the Michelson interferometer for highly precise measurements. Overall, interference not only confirms the wave behavior of light, but also serves as a powerful tool in modern optics, engineering, and scientific research. So that's all, and thank you for listening and participating in today's discussion. I hope these lessons help you understand how interference demonstrate the wave nature of light and how it is applied in various optical technologies. From young double slit experiment to thin film interference and the Michelson interferometer, we have seen how wave interaction can explain many natural phenomena and support important scientific advancements. As you continue studying physics, remember that interference is one of the strongest pieces of evidence for the wave behavior of light and remains essential in modern research and technology. Once again, thank you and have a great day, everyone.